Chapter 8. Models and Descriptions thereof. Thus far, all of the basic mechanics of the ideal field model have been presented with just enough information to avoid turning this paper into a technical manual. What follows are models of possible scenarios with brief descriptions, adding some additional detail which would only have been confusing if introduced earlier. When observing the drawings, keep in mind all of the various ways to look at the model from a particle, to a field, to a system, and beyond. Furthermore, the spheres presented are merely for the ease of modeling the mechanics. To assist visualization, imagine each scenario as ferrofluid on rotating charged spindles, and remember that they are energy density gradients cycling through a wave function. The ideal field model grows progressively more symmetrical in the center. Ejected energy sprays out of the positive vortices and into the negative vortices while the whole model spins. These fountains are the teeth described earlier and strongly resemble the arching solar flares of the sun. Note that this is simply a rough rendition. The vortices would have precise locations, and the heights of the fountains also precise, all according to the internal waveforms. Furthermore, the ejecting lines shown would fan out to create a surface, much like the quintic string shown in image 35 on page 18. A dynamic gearing system is revealed, only adding depth to the quintic string model. Furthermore, the distance and paths of these jets of flux are the classical electron orbitals. Such a model is often seen as outdated in the light of quantum mechanics and the uncertainty principle, suggesting not only that there are no precise orbitals, but possibly that there is no such entity as the electron. However, electromagnetic fields do form these shapes as shown in ferrofluid, plasma labs, and galaxies. Therefore, the orbitals are simply energy density gradients of flux paths, and shared electrons are shared flux with certain properties defined as electrons. Much of the uncertainty may arise because the electron does not exist, but flux does. This is why it is found everywhere. Quote, any discussion of the shapes of electron orbitals is necessarily imprecise, because a given electron, regardless of which orbital it occupies, can at any moment be found at any distance from the nucleus and in any direction due to the uncertainty principle. However, the electron is much more likely to be found in certain regions of the atoms than in others. Given this, a boundary surface can be drawn so that the electron has a high probability to be found anywhere within the surface, and all regions outside the surface have low values. The precise placement of the surface is arbitrary, but any reasonably compact determination must follow a pattern specified by the behavior of the square of the wave function. This boundary surface is what is meant when the shape of an orbital is mentioned. End quote. Wikipedia. S orbits. This flux configuration would be image 11 with its flow from its major axis vortices and minor surface vortices equally balanced, much like the sun. P orbits. These would result if the flow from the major axis vortices were much greater than the minor vortices, similar to the Cat's Eye Nebula on page 13. Even the flow of the minor vortices gets caught up in the spiraling path of the axis flux. D orbits. A. The last four of this row would be a weak major axis flux with powerful minor surface vortices appearing as a four-armed galaxy. B. The first of this row would be that galaxy evolving to have an axis ejection. F orbits. A. The first three in this row would be the result of a powerful major axis flux, with the minor vortices attracted to the flux as in the p orbital, yet having sufficient self-attraction to avoid merging with the axis flux. Due to the significant attraction, the frequency of polarized flux eruptions from the minor vortices are shifted to the two hemispheres instead of being equally distributed across the sphere. Note that the two disk shapes conform roughly to the 19.47 degree anomaly of heavenly bodies shown below. B. The last four of this row adopt the dual tetrahedron geometry, which is the geometry that describes the 19.47 degree anomaly. 19.47 degrees is for a perfect sphere, which no heavenly body is. Yet note that most sunspots occur near the 19.47 degree latitude, as do the dark bands of Jupiter and its great storm. Likewise, the Earth's Bermuda Triangle is at about 23.4 degrees. Lastly, note the hexagram cloud formation at the pole of Saturn as photographed by the Cassini probe. All of this geometry is caused by the tetrahedron. Why is this shape so significant? Because we know that the center of a system tends towards simplistic symmetry, and the most simple form one can have in 3 dimensions is the tetrahedron. If a 4th dimension of motion is added to it, it creates a dual vortex. To add motion, it must be spun. The axis of motion must be drawn through edge to edge, represented by the red dots, not apex to side. Apex to side creates only a single vortex, which is unbalanced with its tiny bottom and wide top. When the tetrahedron is spun edge to edge, it forms the gradient in the middle of the above image. Now, when recursion is brought into play for ultimate balance, a tetrahedron spinning in a tetrahedron, spinning in a tetrahedron, etc., the gradient on the far right is revealed. It creates a dual tetrahedron, a balanced reflection of itself as if it was spun apex to side, one pointing up and one pointing down, to achieve the balance either one could not achieve on its own. Thus, this star is the axis of a spinning tetrahedron through multiple levels of recursion, and the tetrahedron is the simplest, most symmetrical of all 3-dimensional shapes, exactly what the ideal field model predicts for the center of evolved systems. There are only 2 vortices, one of right-hand and one of left-hand spin. In this document, they are named by looking at the positive outward flow. Thus, in images A through M, the violet vortex is a right-hand spin, and the green vortex is a left-hand spin. Note that the orientation of the axis is very significant, for there is a specific vector to it. Any vortex, when inverted, remains the same spin as in image C. It is merely the direction of the flow that appears to change relative to the perspective of the observer. It is important to note that positive and negative are simply vectors of energy flow and not charge. Spin is better thought of as a cycling waveform as opposed to a spinning globe. In classical thought, only direction of spin is taken into account. But now it can be seen that it is not just spin that identifies the particle, but the orientation of its axis. For example, the pairs in image C and D both appear to be spinning towards each other, so one may initially conclude that particle A and particle B in image C are equal to particles A and particles B in image D. Seeing these diagrams, that assumption would only be correct for the A particles, but very wrong for the B particles. This shows that direction of spin cannot be properly defined without knowing the orientation of the axis. Furthermore, the spin also has a flux angle relative to its axis due to the vortex, not a linear spin perpendicular to the axis as in classical thought. The small circles covering the spheres with plus and minus signs marked upon them represent the positive and negative minor surface vortices, which were represented as positive and negative 9s in image 0 on page 3. These minor vortices, when imbalanced, would form centers of charge, cycling around the center of mass of the system as a whole. There are 6 basic parameters of force that are significant in particle interaction. 1. Relative axis orientation. 2. Spin-handedness. 3. Wave pattern. 4. Radius. 5. Energy density. And 6. Angle of interaction. The total effects of these interacting forces directly creates the properties of matter. The following are brief examples. Image A, both axes oriented the same. The axes would repel, the spin would repel, the angle would repel, and only the minor vortices at the right phase would give any hope for such a scenario to attract. Image B, assuming same energy density, these two particles have the same radius, and their axes are oriented to promote attraction and circulation of flux through their axes. Thus, they are pulled together by these, their strongest charges, flux. Also, their angle of interaction is the same. Thus, the bands overlap parallel to each other, allowing the minor vortices maximum interaction, and depending upon their phasing, will assist in either attraction or repulsion. However, despite this, these two particles are of different handedness, making the spin between them conflicting, like two grinding gears. This presents a significant level of repulsion. Nevertheless, the symphony of all of these forces in unison may overcome to create a bond with varying degrees of cavities due to the interference of the two waveforms. Image C, assuming same radii and energy density. These are two like particles, possibly two hydrogens. These two particles are nearly meshed together like two gears, and their axes are aligned for flux to flow from one to the other. However, the angle of their flux cross. The degree of this angle determines the nature of the disturbance. For example, in the image below, the two bands cross at 90 degrees, resulting in significant repulsion. Lesser angles would have less repulsion. However, the minor vortices, represented in green, may be of right phasing and strength to counteract the repulsion, possibly causing an oscillating bond. This may form a phantom vortex, as in image 12. The right side of image 54 shows how complex the crossing angles of flux become when three-dimensional gradients merge. It further shows these energy density levels being the orbitals of classic thought. Image D, assuming same radii and density. These two particles have opposite spin, allowing them to mesh, but their angle of interaction is parallel, allowing for maximum meshing and minor vortex interaction. However, their axes are opposing. But as with any of these models, the attractive forces may overcome the repulsive forces, resulting in a bond. As can be seen, when viewed from the ideal model, bonding becomes a sophisticated form of waveform interaction, as opposed to simply one charge attracting another. Image E, assuming same radii and density. Unlike the previous models engaging side to side, this model engages axis to axis. It engages negative to negative, which may or may not cause an attraction. There is a chance that if it results in attraction, it will increase the vacuum of all the negative minor vortices. However, the opposing direction of the flux, combined with same-handedness, introduces some repulsion. However, the proper strength and phasing of the minor vortices may overcome that.